Welcome to this installment of RAT's Technical Sessions webinar series. We recognize that you have a lot of options available to you for webinars, so thank you for choosing ours. For any colleagues that weren't able to make it to this one, let them know that the recording will be available on our GoToStage channel. The link is on our website and also on LinkedIn as well. Last month, we had a presentation from West Power talking about machinery health management, condition monitoring, which is a fast-growing industry. Next month in August, we have Progressive Sealing and ImproSeal, talking about bearing isolators. And in September, ABB will giving us a rundown on induction motors for industrial usage. Without further ado, I'm going to let Ralph, my co-organizer, present our speaker for this month.
Yes, welcome everyone. Good morning, good afternoon, wherever you're dialing in from. Thank you for joining our webinar series. This is the third presentation that we're giving, and I hope you find that this informative and continue to join in. Let us know if you're experiencing any audio or visual problems. You can send that information in via the chat on the control bar. Also, if you have any questions during the presentation, in the control bar, there is a tab there called questions where you could submit your question. If you are having trouble with your sound or video, you can try closing other applications that are running and other programs that may be streaming and using up bandwidth. Your microphone will be muted through the presentation, but there will be some opportunity to ask your question. I'd like to introduce our guest speaker this time around, and we'd like to hear from Stephen Borle. He's with Group 6 here in Edmonton, Alberta. And Stephen obtained his Bachelor of Science in Materials Engineering at the University of Alberta. And then he went on to complete a Master of Science in Welding Engineering through the Canadian Centre for Welding and Joining. Stephen is responsible for developing new welding procedures, working with different materials and applications for laser-based processes. So at this point in time, I'd like to turn it over to Stephen to tell us about his topic for this time.
Thank you very much, Ralph and Andrew. I appreciate it. So to start off, I'd like to thank everybody for joining us today. I appreciate everyone taking time out of their day to listen to this presentation. So as mentioned in the introduction and the talk description that most of you would have seen, I'll be talking about laser cladding repair today and the automation of that. In addition, I intend to give a bit of a background information on laser processes to make sure that everyone has an understanding of how the process works and how it compares to other coatings commonly used in industry. So in order to better understand what I should focus on in my presentation, we have a few questions interspersed throughout the presentation. So to start, I would like to ask Andrew to start the first poll, which is, how would you describe your role at your company? So I think we'll give everybody a bit of time to answer this poll. After Andrew sees that there's quite a few responses, everyone will be able to see what the exact responses were.
Okay, it looks like things are slowing down a little bit. I'll just give this another 5 seconds. Okay, we're good there. And here are the results.
All right. Okay, so we have some supervisors, reliability specialists, sales, supplier, and engineers. Okay, great. All right, so to continue on and to start to get into the bulk of the presentation, I just want to...
I'm going to turn it over to you. Sorry about that.
Yeah, no worries. We already went through that. So a little bit of history on Group 6 technologies. So we were incorporated in late 2013. We're a dedicated laser cladding and laser heat treating shop with hard material grinding capabilities. We pride ourselves on really increasing automation and helping to bring highly specialized materials and technical processes to a wider swath of industry. So to do that, we have 3 robotic laser cells, and we have ID/OD capabilities, so we can do internals and externals. We can handle diameters up to 72 inches, components that are up to 35 feet long, and we use a rail system for taking large parts in and out of the cells. All of the cells are self-contained, fully automated. So that means the robot's doing all the welding while an operator is outside of it. And that's why we have screens like I'm going to highlight on this picture so that the operator can watch the process as it's going along. We also use a variety of different height sensing technologies and other sensors to help increase the amount of automation that we are the amount of automation that we use. So the really interesting thing that we have recently added to our shop is our 3rd cell. And so the really interesting thing about this cell is it's fully automated with regards to it actually picks up parts. It takes it over to a sensor, which then determines where it is in the cell, and then it takes it over to a preheater. It can set it in the preheater for a determined length of time, or to take it to a certain temperature and hold it at that temperature for as long as it's programmed to do. And then it'll do the cladding, take it over the cladding, automatically do the cladding, and then take it and do measurements, post measurements after the cladding. So it allows us to do very large batches of parts with little to no operator involvement. Because we work with a lot of large components with a lot of hard facing, whether we're taking off old stuff or grinding to a finished size, we have a grinder that allows us to do up to 42.5-inch diameters and 16-foot. It has a 16-foot bed length, but it also has a through chuck, so we can even handle larger or longer parts than that. The last thing I'll go over that we have is a full metallurgy lab. So it has some state-of-the-art equipment, including an automated hardness tester and a really high-powered microscope. And the really benefit of us having this in-house is that we can turn around research and development jobs really quickly. So now, before I get into the processes a little bit more, we have our second question, which is, which of the following processes are you familiar with? So that's going to be repair welding, welding automation or robotics, laser cladding, laser welding, laser heat treating, or none of the above.
Ralph here, just to let the attendees know, you can vote for more than one. So choose any of as many of those that you are familiar with.
Thank you for everybody's participation. I see got a few more votes coming in, and I think it's pretty much stopped, so I will stop the polling now.
All right, sorry, 1 second. I just need to zoom in. We have quite a few that use repair welding or are familiar with it, along with welding automation and robotics. About a third laser cladding, less a fifth for laser heat treating, and then about a fifth that don't have any history or familiarization with those processes. Okay, great. So because we have such a wide range, what I'm going to do is go over some of the processes that we use the lasers for to give everybody a little bit of background information, background knowledge. So to start, the simplest process we do with our lasers, and we use these lasers to do both the heat treating and the cladding process, the same lasers. In the case of laser heat treating though, you're not actually melting the material. So what happens is you're actually heat treating only in the area of the laser beam. And the advantage of doing this compared to bulk hardening processes or batch hardening processes is you really are minimizing the total energy that you're putting into a part, which decreases or totally eliminates any dimensional distortion that you might get with other processes where, you're having to heat an entire part up to, 800-900 degrees or higher and then quench the whole thing. So there's way less distortion, if any distortion, involved with laser heat treating process. Other advantages of it is that it is robotically controlled and a highly repeatable non-contact process. So it's always, if you're doing multiple parts, it's always doing the heat treating in the exact same location. In the video on the right there, you can actually see the laser heat treating being carried out. And in the case of this cell, it's actually a closed loop pyrometer controlled. So that means that there's a pyrometer watching the temperature there at the surface and making sure that it gets it up to close to the melting point, but not actually to the melting point. And that keeps the consistency of the heat treating over long parts, or it's advantageous if you're doing corners, sharp edges, say for gripping teeth or something like that. You can get it right up to the temperature and fluctuate it depending on where it is on the part without worrying about having any unintentional melting. So how is this actually occurring on the part? So what happens, as I mentioned, we bring the surface up to the a high temperature, which is the austenizing temperature. So essentially, we're transforming a bit of the microstructure on the top to an austenite, and then self-quenching is occurring. And that self-quenching just means that the heat is going into the base material around it, and that is what cools down the surface, and it cools down quick enough that you have some microstructure that transforms from the austenite into martensite. So that martensite is a harder microstructure, and that's what gives you the harder surface. That brings me to laser cladding and laser welding, an overview. I am going to use, for the intents of this presentation, mostly use laser cladding. I put the welding in there because sometimes people use it interchangeably. Welding tends to be talking about joining two separate pieces, where with cladding, it's more accurately representing only adding material to a single piece. So for the purposes of this presentation, we're talking more about the cladding, but they're oftentimes used interchangeably. Some people may also use things such as terms such as hard facing or build-up welding rather than cladding, but they're all talking about generally the same thing. And so what's happening with the laser cladding is we use a very high power laser and we'll melt the base material, and then we feed an alloy material, either as a powder or a wire, into the weld pool. And so the benefit of that is you're melting the base material and you're putting molten material in, so you get a good true metallurgical bond, just like you would with any welding process. And so that's a really big benefit compared to some other coating processes that we'll talk about later. So what are the main uses for laser cladding? It tends to be either preventative cladding, and that's where we want to clad a portion for either corrosion or wear protection. And in this case, we can save money because we can use a cheaper base material, yet add a higher value, a more expensive coating just to the area of that component where it needs it. Another area that lasers are commonly used is in the repair and refurbishment. In these instances, what we're doing is we're cladding an overlay to parts of a component that are worn down. And the real benefit of this is we can extend the lifetime of a part that may otherwise be, garbage or thrown out. So that's the gist of what laser cladding is, how it's actually done, which brings me next to just talking a little bit about the materials that we can actually work with. A laser's it has a lot of advantages, including the fact that we have very low dilution. We'll talk about why later on, but that allows us to work on a lot of exotic materials for base materials and clad with a lot of exotic materials. So we do everything from tungsten carbide, stainless steels, Inconel, stellite alloys, nickel alloys, and then other iron-based alloys and titanium. Now, often what's more important than what the most important thing is in selecting material is looking at the actual application. So what we try and do is we look at what type of wear we're seeing for a specific component and then try to come up with a custom solution for each individual part. The reason for that is because you often don't need the strongest material possible out there. because you have to balance a trade-off that you get between abrasion resistance, corrosion resistance, and impact resistance.
Stephen, is there a big difference in cost of these cladding materials? Like in a repair or cladding job, does the material selection make a big difference in the end cost?
Yeah, of course there's the same sunk cost for the time in the cell, but it can have a really big determination on the overall price. Firstly, because some of the materials on here are much more expensive than others. So for example, on the high side would be your tungsten carbide overlays, but even if you look inside of that category, you'll use the tungsten carbide, but you use a matrix material. And that matrix material could either be one of the nickel chrome boron alloys I mentioned, or a stellate alloy. The stellate alloys are cobalt based, and cobalt, this is the spot price for cobalt, about twice that of nickel. So soon, if you decide to use a stellate alloy or a cobalt alloy as the matrix material, that drives the price up quite a bit. So it can have a really big factor on it. The other thing is with stellate alloys, you oftentimes still see drawings in that have it spec'd out. That's because, I'd say in the past it got used heavily in industry, and as the price has increased more and more over the the last few years, you no longer see that happening anymore. The other big factor in what you use is all these materials have different absorptivity with the lasers. So some of them may be a little bit more expensive, but the efficiency of welding with them may go up quite a bit. And so that can all play a big factor on it, on the price of a job.
Yeah, thanks,
Ralph. The next little part now, what I'm going to go into is just quickly comparing laser to other coating processes so that you can see where one might outperform the other, because we're never going to completely replace all coating techniques out there with laser cladding. There's benefits to all of them and they have their uses. So before I get really into that, we're going to start the third and I believe the last poll, and that's just which coating process do you currently use? Laser, MIG, PTA, thermal spray, and HVOF, or chemical deposition methods. That'd be like electroplating, or you can include nitriding or phosphating in there.
Okay, our voting numbers are coming in, still steadily coming in. So looks like it's gonna give it a few more seconds. Okay, I'm gonna stop the polling and we'll see what we come up with.
All right, so we have about, sorry, I'm just expanding my window here. We have about 28% that use laser, others, which probably more manual, so MIG, stick, PTA. There's three quarters thermal spray and HVOF, and then a third chemical deposition methods. Okay, that's great. Thank you, everyone.
I'm kind of surprised. I would have thought more people would have used electroplating. Perhaps maybe if we provide some examples, maybe. Anyways, you will later on.
Well, yeah. All right. So let's take a look at the next slide here. What it's going to highlight is a very general, there we go. What it's highlighting here is just a very general way of sorting out the different processes that are out there and commonly used in industry. So what you can see, and the reason I show this is oftentimes based on the demands of your application, how much you need to build up, or the type of substrate you're using, whether or not it can go through any sort of a thermal cycling, that may determine what you can and cannot use. So this also highlights sort of the area I have labeled as LBW, so laser beam welding or laser cladding. the area that it overlaps most closely with other processes. So that'd be with the traditional build-up welding processes or the thermal spray, and to a much less extent, the electroplating and electroless coatings. This graph has those going very thick. In practicality, I don't think they're often used in industry very much more than a few thou in thickness. So what we can see is, if you have a substrate that you're not able to get above 400 degrees Celsius or 600 degrees Celsius, you may have to use thermal spray or a laser welding, depending on the thickness. Once again, with traditional welding processes, you can get a lot thicker, but we're very close to the same thicknesses or even achieving parity with them with laser cladding. So you can see sort of the overlap where you can sometimes use one or the other, but oftentimes it comes down to performance of the different coating processes, which one you choose. So to go into that into a little bit more detail, what the differences are in the coating processes and the benefits and disadvantages of them in comparison. When you look at laser cladding to a thermal spray process, and we're talking in very big generalities here, right? Because there's a huge variety of different thermal spray types out there. But we can make some generalities, and for the most part, your thermal sprays are really metallurgically bonded, or sorry, they're mechanically bonded. What you have is you have molten particles that are hitting the surface, and what you can see, they hit the surface, and the surface is usually prepped in such a way to help produce a mechanical bond. While with laser cladding, the benefit of laser cladding is we have that metallurgical bond, so it's much more capable of standing up to impacts. It's also, since it's a fully molten weld pool, it's nice and homogeneous. Depending on what type of process you're using for HVOF, it may not be homogeneous at all. It may be very separated out, in different areas, different phases. Also, because of the interaction of different particles, you can get other issues such as porosity or oxidation with the thermal spray process. Now, there are benefits to using thermal spray processes, one being that they often have lower surface temperatures. While we don't heat up the substrate a lot with laser cladding, that's one of the benefits. For example, with a laser cladding, we'll usually preheat something to around 300 degrees Celsius, and it stays fairly consistent at that temperature throughout the process. That's the substrate though. We do have a thin heat affected zone that is reaching much higher than that. Usually in the terms of 20 to 40 thou would be at maximum. Where with the thermal sprays, you're not getting that molten area of the substrate material, so none of it reaches those really, really high temperatures. Thermal sprays processes are also often cheaper than welding processes, so that of course is some benefit. Now, let's take a look at laser cladding compared to other common welding processes. And the next slide, I'm really going to go into it, but the gist of it is with laser cladding, we have a lot less heat input, and this just produces a better quality weld. So other benefits to using laser cladding is that we use automation to ensure that we have accurate and exact repeatability and very fine control of welding parameters. The example here is of a tungsten carbide overlays, and really the reason I chose tungsten carbide to highlight this is it's one of the few alloys that you can actually visually get an idea of how quickly they're cooling down in comparison just by looking at the microstructure. Because what's happening with tungsten carbide overlays is you're putting tungsten carbide, which is about twice as dense as the matrix material. So if you have a very long cooling weld pool, they settle down to the bottom. So that's why you see these settled areas and these voids on the top of the PTA and the MIG processes, where with laser, you have a very homogeneous distribution of the carbides from top to bottom. The other advantages include that, like, these are multi-passes, and you can't even see where there's a difference between the layers in these in the laser cladding. So the next thing that brings up is, well, why? Why does laser cladding have an advantage? Why would we use laser cladding compared to other welding processes, because laser cladding is more expensive than, you know, more traditional welding processes. So as I said, it has the least heat input of any welding process and the highest power density. So why is that? That's because when you're welding with a laser, you have a very concentrated beam. You're only putting energy into that beam area. If you look at these processes on the left of this graph, like oxyacetylene or SMAW or GMAW, which also are known as stick or MIG, respectively, or PTA, plasma transferred arc welding, what happens is you have this arc. This arc is only melting a very small area, and that's where you're doing your welding or your cladding, but the arc is larger than the molten pool. So you are losing a lot of heat through conduction, convection, radiation to a large area of your substrate material, but you're only getting it concentrated enough in a very small area. Well, not a small area, but not the total area of the welding arc. So you have a lot of losses of energy. So what does that do? That means that you put in a ton of extra energy than what you're actually using. For laser, we only put energy into the laser beam area. We don't have these excess losses caused by other heat transfer methods that are present in an arc compared to a laser beam. So as I mentioned, that gives us a big advantage. Now, what is that big advantage? The advantage is we have very low dilution. The table on the left shows you that we're under 5%, where all the other processes are at least, or their, you know, PTA can be very good and very low as well, but it still has much more dilution than what we do with laser. And the other welding processes, you can get upwards of 55% with like submerged arc welding. That is not good. You're losing a lot of material, you have a lot of mixing. So a really good example of that is, say, for Inconel, oftentimes there's a requirement for the chemical composition. We can reach that chemical composition in a single layer because we don't have to do multiple layers to get rid of the dilution of previous layers. Where with other processes, you often need to do 2 or 3 layers because you're introducing dilution every time until you've gotten rid of enough of the dilution that you're back to an Inconel starting range for Inconel.
So Stephen, Ralph here. So dilution is the mixing of your cladding material with the base material. That's what you're referring to as dilution?
Yes. So yes, it's related to penetration. So dilution, to calculate the percentage dilution, would be the area underneath. If you drew a line of where the base material used to be, that area underneath it divided by the total of the area underneath the weld clad and the area above the fusion line, or that line of where the substrate used to be. So for laser cladding, the dilution amount's really low, but we also do thinner layers. So in all actuality, that penetration amount for many of our clads are, you know, less than 5 microns, or right around that line. They're very, very small. Thanks for the question. So now let's get into some of the parts that we are commonly using laser cladding for, that are a little bit, that are along the lines, I think, of what a lot of people here either would already be doing repairs on, or that would be more, that would be familiar with. So these include things such as wear strips and centrifuges, integral wear rings on pump impellers, pump body repairs, bearing lands, centrifuge body repairs. We do dragline swing shafts, boat and ship propeller shafts, pulp and paper titanium mixers, compressor packing sheaths, drag link bore repairs, rotary kin rollers, mining truck spindles, pivot shafts, hydraulic shafts. You know, if it's round, it gets worn out, we can probably fix it up, right?
Stephen, Ralph here again. Yeah, these examples look to be primarily cylindrical. Is laser cladding limited to cylindrical parts?
Thanks. That's a really good, great question, Ralph. So by far the majority of what we do are cylindrical components, but one of the things that we conscientiously chose to do when we set up ourselves was to use robots. So it's common to actually use other movement systems for the laser, such as gantry systems, to move and control the laser heads. But we chose robots because they actually have the greatest degree of freedom. So we can do any type of complex shape as long as we have access to the surface for the laser and the powder to be fed into it. So this can be extremely complex curved surfaces. You can even weld vertically, and theoretically, there's nothing really, you could probably potentially even do overhead welding. So to answer your question concisely, the vast majority are cylindrical, but we're not limited because we use robots in our welding.
Yeah, thank you, Stephen. Just again, reminder to the audience, you can also submit your questions, and we'll have a question and answer time afterwards. Use the control panel. There's a tab there that says questions. You can submit them by that means.
So this brings me into the bulk of what's really new about what we've developed at Group 6 and what I find really, really interesting. What we've gone through so far, is a little bit of background information. So what I'm going into now is automated laser cladding repair. So I know I've talked about how we're automated, and that's, I'm using that terminology because we're using a robot. So now what I'm talking about when I'm talking about automated laser cladding repair is the ability to essentially put something in that's worn out, and someone to hit the green button to go, and then everything gets taken care of with no input. That's what we're ideally working towards. There's still some operator input at this point, but we're working towards essentially having none. So what I'm going to go into is explaining exactly what all the different steps are. But first, once again, we're just going to talk about robotic automation and repair welding and how they fit together. So the robotic automation, like I've mentioned many times, it's very repeatable. That's a huge advantage. That ends up being a disadvantage when you're doing one-off parts or repair parts. Now, other advantages of using robots is that they're capable of being used for processes that you can't do manually, such as laser. Laser's too much of a high-powered process. You can't do it manually. There's the other advantage of robots is they can be used to do the same task over and over again, boring, repetitive tasks that someone wouldn't want to stand there and do. The other thing is it allows operators to set up a job, and then while the robot's doing the welding, they are outside of the cell and they can either do another task or prep the next job. So there are disadvantages though of using robotic automation. One of the biggest ones I see in the parts we do routinely is that robots have been set up and they were developed really for new high volume production parts. If you look around an industry in Alberta and the local area, we don't do a lot of really, really high volume parts. Now, if you go look in something like the automotive sector, they've been using robots for decades longer than us, and they use them in way higher quantities because they're literally doing the same welds or the same 5 welds on the same cars for years at a time. It's really set up for that. Where doing one-offs, it's not. So we've had to develop methods, techniques, and tricks to adapt robotic welding for these one-off parts, or for parts that instead of doing thousands, we're doing 5, 10, tens of. So other disadvantages are when you do have difficulties with the codes, with the robots, it oftentimes is more difficult to do the troubleshooting. There's also the high investment cost, and it can be very hard to find employees with the skills needed. So now let's look at repair welding. Why do we want to repair parts? Well, the big thing is we want to repair parts that are not easy to source or that have really long lead times, right? A lot of the stuff that's used in the pumps, compressors, they're made overseas, they're made in Europe. Especially now, you can see that when some of these the trade links have broken down a little bit during COVID and stuff, you can see that can become a difficulty is when you're relying on parts coming from overseas. So we want to be able to repair them so that we can use them again rather than having to replace them. And the benefit of that is we can do it locally, and we can often do it in much shorter periods of time. The best examples of that is just this picture here in the center. You get a guy with a torch to go out and fix a bucket while it's still on a machine, rather than having to, replace it or to send it to a shop somewhere to get done. The other advantage of doing repair welding is we can actually use alternative materials to what it was originally built out of, to decrease the wear that we're seeing in the future. So for example, if you have a centrifuge part that is continually getting washed in the same area, we can rebuild it we can rebuild that with, a butter layer or a corrosion resistant material, and then at the top just do a layer of tungsten carbide or other wear resistant material. Now, why can repair welding be difficult, and why do we sometimes not do it? It's because it's really time consuming, and that tends to increase the cost quite a bit. And why is it really time consuming? Because it either needs to be done manually, because you can't really effectively automate it. To do repair welding, every individual part is different, and that makes it very, very difficult. For automation, it's always good if it's a very simple shape, or it's much easier to automate if it's a simple shape, or even if it's not a simple shape, but if you have hundreds of them that are the same shape, it might take you a while to do the first one, but you make that up on the next one and the next one, then it becomes efficient. So when I mention it's not really efficient to automate, well, what do we do right now? If it's, we still, obviously, a lot of us use repair welding every day. So what are we doing currently in industry? So if we look at it, we either use just a manual welding process, but the personnel cost for this can be high as well. If a skilled welder is not cheap, and it's getting harder and harder to find welders, especially in the very long term. I do a lot of work with the CWB Association, and one of their big worries in the future is continuing to get people into the welding trade. So it's going to get harder and harder to find good welders. Another thing is consistency can be an issue, right? No matter how good the welder is, you cannot always be traveling at the exact same speed or keep your gun at the exact same distance away from the part that you're welding on. And only, as I mentioned before, you can't do, say, laser welding with a manual welding process. So that brings me to the next 2 points, which are point touch-up and offline programming. So these are sort of two areas that you can potentially use for an automated process that's using a robot to try and do repair. Now, a point touch-up, what it's essentially doing is you send whatever part you have out there, and you teach the robot each of the locations that you want it to go to for the welding points. So you have to have a part in there, and then you manually touch it up by moving the robot using what's essentially a controller. Now, this is very slow. The time it takes to touch up points is way, way longer than what it does to actually do the welding. You also need a skilled operator that knows what they're doing. And that whole time that you're doing point touch-up, you can't be welding because you're using the robot in the welding cell to do the touch-up. So that really decreases the productivity. So offline programming, the benefit of offline programming is it allows you to do the programming, but not in the cell. So there are benefits to that for sure. But what I've experienced, what I've seen, is the offline programming, what it is it's essentially a 3D representation of your robotic cell and whatever you're welding. So first of all, you have to get that, what you're welding in a 3D model or whatever, and then you can do offline programming. But the downside of that is it's really imperfect. Everything is done theoretically in this 3D model, and then you send it out into the real world, and there tends to be a mismatch between the actual and the theoretical of what you're doing in the program, the offline program. And then that just involves more time fixing that when you're actually out at the cell. The other downside of this is it takes a really highly skilled operator or programmer to work with these programs. And the programs are expensive in themselves and oftentimes come with yearly costs to keep them updated. And then that brings me to the fourth area, or fourth method for repair. And that's just to pre-machine down to a known diameter. And you know what, that's good. It works well, it's consistent. As soon as you've machined it down to a known diameter, you can treat it like a new part and it becomes much easier to automate. But the downside to that is you're adding that extra process in of doing the machining. That drives up the cost. It increases the turnaround time because now you have to do a machining step in between. And you have less retained base material, and you're now going to have to build that base material back up. It doesn't make much logical sense to remove material just to add it back in. So that brings us to what our goal at Group 6 is. And our goal is to fully automate the repair process. So by fully automating the repair process, I mean we want to minimize the operator input, streamline the process, eliminate the need for pre-machining, decrease the welding time and the material consumption, and retain the maximum amount of base material. And if we do all this, we're going to increase our efficiency, quality, and speed while decreasing the cost. So it's a win-win for us, for everyone that we work with. So we dreamed up this idea a couple years ago, and to start working on it, we've partnered up with a couple other groups. That would be LIMDA, which is the Laboratory of Intelligent Manufacturing, Design and Automation, and the CCWJ, which is the Canadian Centre for Welding and Joining. So we started this project about 1.5 years ago, and we'll be finishing it up in the next 6 months or so. So we decided to start by focusing on one part in particular. And so that's the part that I'm going to walk through, the steps that we actually take, or the steps that are needed to automate the repair process. So the part that it is called a bent housing. Now, this is used on drilling strings to change the angle of drilling. So what happens is there's one area when you're doing directional drilling that all of a sudden you have an angle change. So in this picture, it's right here. On this model, it's right here. And then you can see this pad right here. That's where the angle is on this video that I'll show in a second. So what happens is you put weight on the entire drilling string, and then there's a force against this pad. And when the force is against this pad and it's being pushed down this way, it drills in the opposite direction. So you put a lot of weight, which is translated into the side, and that's why they actually build up this area with a really wear-resistant material, such as tungsten carbide. Now, even though we were using tungsten carbide, these can sometimes only last hundreds of hours when they're actually in operation. And the interesting thing about drilling strings is they also want to drill, they drill straight as well. My apologies, I'm just trying to get the video to start playing. So they also drill straight, of course, at some portions. And so what happens is you'll see in this video is then they actually rotate the entire drill string while pushing down once again. But what you see from the illustration, and there's that wear pad, at all times it's in contact with the outer edge of the weld bore. So it's constantly seeing wear, no matter what type of drilling is going on. So that brings me to, what does a new part look like? A new part takes 20 to 30 minutes of laser time. It's easy. A guy will set up, normally there's big batches of the exact same part. A guy will set it up for a single part, and after that, an operator is just taking a part in and then taking it out when it's done and then replacing it. And they will do that for days on end. So it's a really efficient process. Now, let's take a look at what happens when we have a worn out part. So we'll get it back from the field and it will have all types of different wear patterns on it. Oftentimes it's this parabolic shape, right? Because that's the furthest corners where it's making the most contact and the most pressure on it. So you get this parabolic wear. But then as you can see on this one, it's worn across the entirety of the pad. And you can see the sort of the difference. When this was new, this would have been flat along the top. You can see how much it's actually worn down at the front of the pad here. And on the right is just a graphical illustration of what's going on. And the wear, so what you can see is the wear is never consistent. It's always going to be slightly different. The depth might be different. The width of that parabolic shape is always going to be different, which makes it very hard to make tool paths. You have to make individualized tool path for each part. So before we started out this project, we're still repairing them, but we're sort of going about it in, I would say, a fairly inefficient way. So what we would do is we'd receive that part worn out and we would grind it down. We'd grind it down to have a nice surface, and then just the extremely low area would be left, but we'd remove any hard facing that was previously on there. We'd then build up that area with Inconel, the low spots, and then build up Inconel across the entirety of the pad. But because we're not controlling for the difference in the depth, we would control the laser to follow the difference in the depth of the surface, but you can't, or we were unable to, make sure that we put less in the middle than we would on the outside. You'd end up having a lot more material along the edges of these worn areas than the center. So you'd have to go through another grind stage to bring it back to what would essentially be the nominal diameter of a brand new part. And then we would continue on by applying hard facing in the traditional method that we would with a new part. So they greatly varied in the length of time to do them, but roughly you could say to do a repair would easily be 4 times as long for a repair, and you'd need a lot more material to do the base buildup, and you'd need to do an initial grind and a grind midway through. So the time for it is way longer, and you have to go between the cladding and the grinding stages twice. So now I'm going to explain how you go about doing automated repair. So I broke it down into 4 general steps or areas that are all work together, but are all sort of done in separate ways and can be done in multiple different ways. So the first one would be the acquisition of the shape of the worn component. And before I get into that, I'll just go through all the steps. After we get the shape, we need to compare it. So that's called registration. Then we look at the repair volume extraction. That's taking a look at the difference and finding the area we need to actually repair. Then path planning is the tool path planning. So that first step we come back to is the acquisition of the worn shape. So if we look at it, there's a few different ways to get that shape. You can use CMM machine or something like a laser scanner or CT scanner. The laser scanner is by far the most commonly used. It works super quick, super efficient. This is an example of a scan of a bent housing. This is the wear area right here that I'm just going around. And so with the program, or with the laser or the CMM, they normally come with programs that allow you to acquire a point cloud file and then either convert it into STL files or solid bodies, depending on what you're working with later on. The next step is we have a worn part. Now we need to compare it to a new part to figure out what has changed, and we have to do registration to do that. So what is registration? Registration, the goal of it is to find the relative positions and orientations of separately acquired data. So that means you're getting the data from 2 different points. In this case, for a worn and a new part, we have a model of a new part, and we have the model that we got from scanning it for the worn part, and we try and fit those together. So to do this, we use algorithms that attempt to minimize the distance between 2 models' corresponding points. And there's quite a few different ways of doing it, but out there, most of the time as well, there are sort of pre-built programs that can do that for you. It just depends on getting everything to work together well. So this is the example of using a built-in algorithm to auto-align our model of a fixed bend, which is the gray one up here, to the worn surface that we looked at earlier. And in this case, what I did is I aligned them, and then I used a heat map to show the difference between the heights. So anywhere that's blue is below the nominal model on the worn model, and anywhere that's red is above. So in this case, we're really interested in the pad area, and you can see how much it's been worn down on both sides.
Well, Stephen, I was just curious. Now, that's worn down obviously outside of the pad area. Now, would you be building that up with apparent material as well?
So in this case, we probably wouldn't be. It is possible too. In all actuality, this part was used to develop the process. So it was a scrap part. If it was worn down too much, it would have just been scrapped at that part. But you could use the same process to build up everywhere entirely. Well, in this case, we only focused on the pad. But what you bring up is a really good point leading into the next section, which is you have to have a program that's robust enough to, when you do the separation, to only concentrate on the areas that you're interested in. And what I mean by that is when we're looking at the repair volume extraction, if you look at the last slide we're looking at, all these other areas could be considered repair volume if you're doing it fully automated. So you have to have some way of being like, no, I want to only look at that pad area that I need to fix, that I want to fix, or I want to build back up. So the next step is that repair volume. I'm not going to go into this too in depth because there's a lot of different ways to do it, and it depends on what type of models you're starting with, what type of point acquisition you're using. But essentially the two main ones, or there's two main groups that everything can be sort of go under, and that's either using a Boolean algorithm, which is essentially you just have a model, a CAD model, and you're comparing it to a model of your worn part. So in this instance, the worn or damaged part is right here, and so they subtract the area of this from this model, and that leaves only the worn area, or in this case they call it a defective portion of the part, which was right along that edge, and that's going to be the repair area. The distance-based filtering, it essentially looks for where you see these blue dots, or let's say purple dots. That's a combination of blue and red dots that are closely overlining with each other. But then you see this area of red or pink dots. Those dots are further away than average from these other purple dots. And so it uses an algorithm to find all the red dots that are further away than a certain distance away from blue dots, and that's how it gets the repair volume. It's quite complicated and convoluted, but it's just a generality. What I'll show you is sort of the example of what we do with the fixed bend housing, and this is using a distance-based example for the fixed bend housing. On the left is the scan of the pad area, and what I've just done is I've taken those scans and I've flattened them out. So in this case, the nominal diameter essentially is that red line that you see, and the worn surface is the green dots that you see. So those green dots and the area between the green dots and the red dots, that in this case is our repair area. So we now take that repair area and we develop the tool path planning and the welding. So this also is very part specific, very, what part you're repairing and what you're actually using to do the repair, what type of robot, what type of process. But essentially what it does is it takes algorithms and then it determines the where rebuild up area and determines the best method for building it up. So in this case, all these differently colored lines, they're all different tool paths. So each one is a different tool path. So there's multiple layers. And so if we break this down, we can see the first pass at the lowest layer is this blue one. And then what we have here is we have a little bit wider that we go on the second layer, and then we get to a constant height from the lower layer and it goes straight along, and then it goes back up the side. Now the reason that that's really neat about what we're doing and what we've developed with our tool algorithm is because you can see, especially for that first layer, the amount that needs to be built up, sorry, I should have explained, up here would be the nominal diameter, and then this is a graphical representation of the worn surface. But you can see the area that you need to build up between the blue and the next layer is less here and more here. So we actually use an algorithm that speeds it up at the edges and slows it down where it needs to build up more. And what that does is that gives you, we can plot that on the left, and on the left that's showing the different speeds across one single layer. So in this instance, it's the first layer, and so you can see that it goes fast at the side, then it's more worn out in the middle and at the front and the back of the pad, so it slows down at those points and then picks up again. Where in the center, there's not as much wear, so it can go quicker. Now, the tool path also must then be converted back into a language or control system that works for the welding equipment being used. So it's really specific to individual companies and how they decide to do it. So what I have here is a video sped up of it doing it's right there. It just did the first layer 3, and then it skips over to the third layer, but you can see the area being clad is going now wider than the previous clad path there because it's moved up to the higher layers. And you can also just see that here on the right. Layer 1 is a little bit more parabolic shape, but then we filled that out and it would have gone slower or faster in the middle than it did on the outside, which is why you can see a bit of a color difference. And you can still see that in layer 2, it's gone out wider than the first layer. And then layer 3, it's even higher. And you can see this slight discoloration. That's actually just coming from the changes of the speed. It's still going, it's going slower in the middle to try and build that up to the nominal diameter and just thin at the edges. And then at the last layer, without doing any steps in between, it now has a nice consistent layer and height across the entirety of the diameter.
That video is amazing. How long is that total elapsed time for the weld process?
So as I mentioned, like for a brand new part, it'd be 20 to 30 minutes, but with worn parts, it really varies greatly based on the amount of wear. But I think it's reasonable to say and to estimate that the time a part would spend in the cell is at least cut in half when you use the automated repair process compared to an older method, and it easily cuts the powder usage for the buildup material by 25 to 50%.
Okay, and so I just want to mention we've got 2 minutes left until the end of the hour, so we do have one question to go through.
Okay. Yeah, I'll go through this. So now what we're doing is we're just looking at another part that we used it on that's a lot, I'd say is a lot more related to a lot of people that are probably, or people are more familiar with that are sitting in on this presentation. So this is a centrifuge bowl and hub, and the gist of it is what you can see is a huge amount of wear in this area next to the castles. The hub, at some points, it's less than 1 millimeter thick. And so what we did is we applied our process, first of all, by scanning it and then doing the alignment, everything we talked about. And then we got an optimized tool path. And that's why you can see these parts that look like patches. That's because those are the extremely low parts. The next layer will cover more and more until you get uniform going around the entirety of the diameter like we saw with the fixed bends. So this is starting out a little bit further through. Now it's gone close to the end. The reason that it's building up on this side before building across entirety of everything is because it was so much more worn down on the right. This is just a side view of that. We had about 8-9 millimeters of buildup. In this case, that's over 8 layers for this material. The full part completed is here on the left with the clad. In this case, the company did want to machine it down to a diameter and then apply an HVOF on top. But the advantage of doing it with lasers, we could have also, just used a wear coating at that point and not having to do the intermediate machining. But in this case, it was something that the customer wanted, and we do whatever the customer would like. This brings me pretty much to the end of the presentation, but really now it's just what are the next steps? And so the next steps are we need to develop this process, the automation process of the repair for a larger number of components. So essentially what I've shown you is it works well. We can use it with any, at the state we're in right now, with any cylindrical component. So now we need to work with, components that are, say more complicated, like a double barrel, or that have, faces as well as diameters, or in this case, which is really unique about using the robot, is parts that are either that are very unsymmetrical and that we can't rotate in a chuck. We can actually put them in place and then rotate the head around to do the repairs. So we need to we're now working on developing the automation and bringing it over to a wider range of different parts. The big goal is to make the process cost effective enough that we start to actually repair parts that people don't even think about repairing right now, right? If you automate this all and it can run by itself with no operator, you can all of a sudden do a lot of things that you're just not effectively able to anymore. Other neat thing we can do with the laser is we can do layering techniques. So we could intersperse wear resistant material in different layers or in different areas, but then use corrosion resistant in another area, or just build up areas in another one. And the big steps to really getting this super efficient is to decrease the amount of operator input that we have. We're at the point that we still have a bit of operator input, but we're confident that we can get it to the point where it's nearly as simple as hitting that green button and walking away and coming back when it's done. So I just need to thank and acknowledge some of the project sponsors, which were NSERC and NRC. And thank you, everyone, for listening to me today. We're going to ask some questions now, but feel free to send me an email or give me a phone call if you have any other questions.
Okay, so there was one question from Raj Lakhani. He's left now, so I'm going to read his question to him. Hopefully he gets to this video later on and he can see this. So have you ever encountered any issues with microcracking, especially in tungsten carbide coating? And also, is it economically feasible to do laser cladding on a large surface component? Those are his questions.
Yeah, it's a good question. With the tungsten carbide, with laser cladding and tungsten carbide, if you go, anything over a single layer, you do get cracking. It's almost inevitable. That's something that's well known and not normally an issue, because when you go with something that's as hard as tungsten carbide, you tend to get cracking. But once again, if you're not using it as the buildup of the strength of the material and only as a wear coating, that's not really an issue.
Okay, thank you. So at the conclusion of this presentation, you'll get a survey, and if there's any more questions or any more information you want from Group 6, just let us know.